Chapter 16.3 Forecasting with Regression Analysis. The forecasting methods that rely on smoothing techniques strive to average out the random component in the historical time series. As we have discussed, a potential drawback of this technique is that they perform well under static conditions, that is, when future periods were much like the last. However, these techniques don't perform well with data that are changing or content trend or seasonal pattern. Forecasting error can be relatively high under this condition. One solution to this problem is to consider under the simple and multiple regression techniques we discussed in chapter 14 and 15. This method will often provide better results when trend and or seasonal components are present. Trend projection. In chapter 14, you learn that a simple linear regression describes a straight line that best fits a series of ordered pairs x and y, each of which pertain to a single observation. This regression line explains how a change in an independent variable x influences a change in a dependent variable y. In this chapter, we will use this straight line to describe the linear trend component of our time series. Using trend projection, we can then project this trend line into future periods to develop a forecast for the time series. Figure 16.6 shows the trend projection graphically. The x-axis displays the time period, which is for our car sales data is quarters. The y-axis displays the forecasted variable, which is number of cars sold per quarter. The blue dots indicate the 12 quarters of car sales data from table 16.1. And the solid red line represents the regression line that best fits this data. Finally, the dotted red line is the trend projection, which provides us with a forecast for car sales in future quarters. The equation for the trend projection line takes the form shown in equation 16.6, where y cap t is the forecasted value of y given a value of t. T is the time period. B0 is the y-intercept of the trend projection line. B1 is the slope of the trend projection line. The slope of the red line, B1, in figure 16.6 measures the rate of which car sales change from one quarter to the next. The y-intercept, B0, indicates the level of car sales at which the red line crosses the vertical axis. Equation 16.7 and 16.8 can be used to calculate the slope and y-intercept respectively. Table 16.8 shows the summary calculation needed to calculate the slope and y-intercept for our sales car time series. The regression equation that describes the trend component through our car sales time series data is therefore as follows. Y cap t equal to 115.5453 plus 2.7238 t. According to this result, sales increased an average 2.7238 cars per quarter. It looked like business at Brandywine Ford is getting better over time. We are now ready to generate forecasts using trend projection for period 13. We do this by substituting 13 for the variable t in our trend equation. Y cap 13 equal to 115.5453 plus 2.7238 times 13 equal approximately to 151 cars. Our trend projection forecast for period 13 sales is 150 cars. Figure 16.7 illustrates this graphically. The green line shows that our projected trend line in period 13 corresponds to forecast sales of 151 cars. We can also forecast sales for period 14 if we choose as follows. Y cap 14 is equal to 115.5453 plus 2.7238 times 14 equal to 154 cars. However, recall that the further out into the future we project our trend line, the less reliable our forecasted value will be. For example, as I explained earlier in the chapter, we usually give much more credence to tomorrow's weather forecast than we do to the 10 days in 10 days forecast. Too often, our plans spoil watching what once was a great 10 days forecast turn miserably when the fateful day arrives. In order to compare the accuracy of this forecasting method with our car sales data to the smoothing method that from earlier in the chapter, we need to return to our friend the MAD. We do so by calculating the forecasted car sales for periods 1 through 12 using the trend equation and then comparing this value with the actual sales. For example, the forecasted for period 1 is found by stating t equal to 1 in the trend equation where y cap 1 is equal to 118.3. Recall that with a regression analysis, the forecasting error is known as the residual, which is just a fancy word for the difference between an actual value and a predicted value. The residual can be found using equation 16.9, where EI is the residual of the ith observation in the sample, YI is the actual value of the dependent variable for the ith data point. Y cap I is the predicted value of the dependent variable for the ith data point. For period 1, the forecasting error is therefore given as follows. E1 equal to Y1 minus Y cap 1 equal to 97 minus 118.3 equal to minus 21.3. Our forecast using the trend equation predicted sales that were 21.3 cars higher than the actual sales in period 1. This forecasting error is shown graphically in figure 16.8. The forecast and forecasting error calculation for the remaining period are shown in table 16.9. The MAD for our trend projection forecast is therefore as follows. MAD equal to summation of absolute value of YT minus Y cap T divided by N equal to 165.2 divided by 12 equal to 13.8. This forecasting accuracy beats most of the smoothing method except for the 4 period simple moving average, which had a MAD equal to 11.1. Checking autocorrelation. The regression model that we have been discussing in this section relies on certain assumptions holding true. One such assumption is that the residuals are independent of one another. We will use the following example to clarify this concept. Suppose that on the first 5 quarters of your job as the new car sales manager for Brandywine Ford, you had provided your boss with the forecast shown in table 16.10. Also shown are the actual sales of your forecasting errors for each quarter. In table 16.10, the residuals are not independent of one another. I say this because by knowing the residual for period 1, I can predict the residual for period 2. This pattern holds true for other periods as well. This term autocorrelation is used to describe this condition when residuals are not independent one another. To determine the presence of autocorrelation, we can use the Durbin-Watson statistic, D, which is shown in equation 16.10, where D is the Durbin-Watson statistic. ET is YT minus Y cap T, or the residual for period T, and the number of values in the time series. The Durbin-Watson statistic ranges from 0 to 4. A value of 0 indicates perfect positive autocorrelation. A value of 2 indicates no autocorrelations. A value of 4 indicates perfect negative autocorrelation. Positive autocorrelation is present when we observe a pattern of positive residuals in succession, such as those shown in table 16.10, or a pattern of consecutive negative residual in succession. When these occur, the consecutive residuals tend to be close to one another, making the numerator in equation 16.10 relatively small. This in turn makes the Durbin-Watson statistic approach 0. Table 16.11 demonstrates the case of perfect positive autocorrelation using the data from table 16.10, which occurs when the residual from each period are equal. The Durbin-Watson statistic for perfect autocorrelation is then as follows: D equal to 0 divided by 2000 equal to 0. Negative autocorrelation is present when the consecutive residuals are far apart from one another, causing the number of equation 16.10 to be relatively large. Because residuals tend to oscillate around 0, large swings in consecutive values tend to alternate between positive and negative sign. In the case of perfect negative autocorrelation, we see forecasting errors such as 20, minus 20, 20, and minus 20, as we subtract the difference between consecutive individual. 20 minus 20 equal to 40, and square the difference. 40 square equal to 1600. The numerator in the Durbin-Watson statistic approaches 4 times the the denominator of 20 point square equal to 400. As a result, perfect negative autocorrelation is measured with a Durbin-Watson statistic equal to 4, its upper limit. However, this type of residual pattern is not very common in practice. When calculating the Durbin-Watson statistic from a sample to detect autocorrelation in the population, the value of D is subject to sampling error. To test the presence of autocorrelation in the population, we need to perform or take a deep breath hypothesis test. To obtain reliable result for this test, we need a time series that has at least 15 observations. Because our car sales example has only 12 periods of data, we will not test this time series for autocorrelation. Rather, we will use the following example. Union membership in the United States over the past 16 years has experienced a general decline. Table 1612 shows the percentage of the labor force in the United States that belong to a union over a 16-year period. This data can also be found in the Excel file unionmembership.xlxx. A graph of this data is shown in figure 16.10 and illustrates a decreasing trend component over time. The linear trend line from Excel is shown in red in this figure. Because negative autocorrelation is rarely seen, we will focus on the detection of positive autocorrelation. With that in mind, our hypothesis statement becomes the following. Null hypothesis: no positive autocorrelation is present. Alternative hypothesis, or H1, positive autocorrelation is present. We will conduct this one-tail test using alpha equal to 0.05. To calculate the Durbin-Watson statistic, we will rely on PA-STAT, which provides this value for us. We'll also show you how to calculate it with Excel using the following step. 1. Open the Excel file unionmembership.xlxx or enter the data shown in figure 16.11a. 2. Go to add in and select PSTAT, select regression, and then select simple linear regression as shown in figure 16.9a. 3. Fill in the simple linear regression dialog box as shown in figure 16.11a. Be sure to check the Durbin-Watson statistic in the output option area of the dialog box and then click OK. PA-STAT create worksheet label compute and residual that I have combined in figure 16.11b. We will use the information to demonstrate how to calculate the Durbin-Watson statistic manually. PA-STAT also creates a worksheet labeled Durbin-Watson, which contains the value of the Durbin-Watson statistic as shown in figure 16.11c. According to figure 16.11c, the Durbin-Watson statistic for our union membership time series using equation 1610 is therefore as follows. D equal to 0.8449. This value can be calculated directly from Excel using the regression output in figure 16.11c. We will start with the regression equation for the time series. Y cap t equal to 14.13 minus 0.16446 t. Next, we will calculate the predicted union membership for period 1 or 1997 along with the residual for that year. Y cap 1 is equal to 14.13 minus 0.1648 times 1 equal to 13.97. E1 is equal to Y1 minus Y cap 1 equal to 14.1 minus 13.97 equal to 0.13. Next, we will show the same calculation for period 2 or 1998, where Y cap 2 is equal to 13.8 and E2 equal to 0.20. Finally, we will take the difference of this residual and square the result. E2 minus E1 square equal to 0.07 square equal to 0.0049. We will repeat this calculation for the remaining years of our time series with the help of Excel, for which we should all be grateful. The results are shown in figure 16.11d. Using this calculation and equation 16.10 to determine the Durbin-Watson statistic, we have the following. The slight difference between this value and the one found using PH-STAT can be attributed to minor rounding in the calculation. We need to compare this number with the critical values for the Durbin-Watson test, which can be found in Table 9 in Appendix A. An excerpt of this table is shown in Table 16.13. The critical values shown in Table 16.13 are for a one-tailed test, which we have in our union membership example. The value of k in this table refers to the number of independent variables in the regression model. For our union membership example, there is only one independent variable or period number, so k equal to 1. The value of n refers to the number of observations in our time series, which for this example equal to 16. The Durbin-Watson test used two critical values, dl and du, which for our example are 1.10 and 1.37 respectively, or highlighted in yellow. We use the following decision rule to state our conclusion. If d less than dl, we reject null hypothesis and conclude that a positive autocorrelation is present. If d is between dl and du, the test is inconclusive. If d greater than du, we fail to reject null hypothesis and conclude that no positive autocorrelation is present. Because d equal to 0.8536, dl equal to 1.10, we reject null hypothesis and conclude that a positive autocorrelation exists with our union membership time series. As a result, an important assumption of the regression model is violated in this example. Time series regression models tend to be particularly susceptible to autocorrelation because the data value from one period can often influence the data value in a later period. The presence of autocorrelation makes the significant test for the regression coefficient unreliable. One possible solution to address autocorrelation would be to identify additional independent variables to add to the model that would help explain the variation in the dependent or forecasted variable. This would result in a different series of residuals that might not exhibit the pattern of autocorrelation. Thank you.